The House of Sultan and Sons Private Limited and Method AI extend a very warm welcome to all the participants of today's Artificial Intelligence webinar. It feels nice to have you all here, and we thank you for that. A bit about the House of Sultan first. Pioneers in the field of book publishing in post-independent India, we cater to students from pre-primary to university level, churning out over 600 regular titles, besides adding new ones to our stable year after year. Known for competently written, elegantly produced, and reasonably priced books, our publications are widely prescribed in reputed schools and colleges across the nation as well as in some neighboring countries. Our authors are distinguished academicians, professors, and educationists with vast experience and expertise. We are proud to be associated with them. I now introduce you to the host of today's webinar, Dr. Sachin Gupta. Besides authoring artificial intelligence and data science textbooks for classes 9th and 10th, Dr. Gupta is Dean, Research and Innovation, Maharaja Agrasen Institute of Technology, Guru Gobind Singh Indraprastha University, Delhi. I take pleasure in informing you that Dr. Gupta has added another feather to his cap. His latest book on AI, Decoding Artificial Intelligence, has won the Outstanding Contribution to AI Literature Award recently. A great feat indeed. Besides, Dr. Gupta has also been HOD, Computer Science Engineering and MCA Department, Dronacharya Group of Institutions, Deputy Director and Head, Computer Science Department, Chandraprabhu Jain College of Higher Studies, affiliated to GGSIPU, Delhi. With a teaching experience of over 20 years, which includes teaching undergraduate students, postgraduate students, and researchers, Dr. Gupta's academic pursuits have been fairly meritorious, winning him several awards, distinctions, scholarships, including the Certificate of Academic Excellence by GGSIPU. Dr. Gupta has also contributed to various journals, conferences, and books for schools and higher education, both nationally and internationally. His achievements are truly commendable. May I now request the man himself to take you through today's session, Dr. Sachin Gupta. Have a great day ahead. Thank you.
Thank you. Thank you so much, sir. Thank you for the introduction. We are going to discuss in a series of lectures. We have covered the syllabus for class 10 across artificial intelligence. A lot of topics have been covered, covering almost a complete curriculum. But there was one topic that several faculty members have requested that to be discussed, that is evaluation metrics in machine learning. And that is what we are going to discuss today. It would be a two-part series because regression models have their own set of evaluation metrics, while classification has a different set. So we'll cover classification later, but for today we are going to take up the session on regression. In case if you have any queries, please feel free to ask while we discuss this on. I hope my screen is visible. Your chat window is my window to the queries. So you can post any queries in the chat box whenever you have one. I hope everybody is ready to begin. So here we go. Before understanding the metrics in machine learning, it is very important to understand the concept of bias and variance. This comes across in several forms. Several people talk about it, but it is one of the least understood areas in machine learning, because bias, in very, very simple words, it represents the distance of our predicted values with the original values. Let's go into machine learning first. Machine learning basically is the task of teaching a machine to understand the data which we already have, to try and make predictions about something that we already do not know. So there come in two things, that some values we are trying to predict and some values we had original available. So bias deals with the training data only. Most of the machine learning models work with two parts. They would be, we split the data into training and testing so that we'll be able to train the model, and then we are going to able to check what is the performance of the model on the testing data as well. They actually give rise to two different metrics. First of them being bias. Bias compares how much our data is working in accordance with the training data. So the distance of our predicted values with the original is the bias. Variance is the distance of predicted values, how much the predicted values are scattered from each other. That are they close to each other or are they very variable? If all the predicted values are very close, that leads to a problem that we'll discuss later. But for the time being, let us look at what it looks like. So people ask that what is the good quality for a model, whether it should be having low variance or high variance, or the best model is the one which is low variance and low bias. There, low bias means the predictions are close to the original value. High variance means the predictions are far distance from each other. So with high variance, we can actually show the value that is spread across the complete target space. With low variance, we are saying that they are close to each other. With high bias, the predictions are far off from the original value. All right. And low variance predictions are close to each other. So this basically allows us to understand that a model would be good whenever we have a low variance, low bias. That would be bang on the target. We don't have to worry about it, that how this is going to work. But there's a problem, that can we make a model low variance and low bias both? There is a problem that bias and variance are usually counterintuitive. And I tell you why. When I say errors due to bias, that means the model is too simple to represent a certain situation. That means it is not able to understand, it's not able to capture the information in the complete training set that we have given. It cannot catch all the details. It's missing out some details in the training data also. If the bias is high, it will cause underfitting. That means if the errors due to bias are high, that is the model is underfit. The model is missing something important. Errors due to variance means that the model is not generalized enough. I'll show you that something. What do I mean when I say a model is simple or complex? This is very important to understand. Mathematically, you would be able to say that any equation which is linear would have no powers of x. If x is a determinant or if x is a driving variable, then if x has got no powers, it's like the equation of a line, y equal to mx plus b. There are no powers of x. The line is a straight line. But the moment we want our line to be curved, any curvature, like the equation for a circle is x square plus y square equal to r square. That is in terms of square, powers of 2. So this model is a bit more complex than the first one. So I hope you understand what model complexity means, that our mathematical equation for representing our data values, if it is linear, it would be having no powers of x, it would be 1. If it is increasing in complexity, the powers of x would start increasing. It might be a model having a lot of curves. In that case, the powers of x may go from x to x square to x cube to x to power of 4 also. So this model is very complicated. Now, this model was not capturing the entire set of details. That means it missed out on certain points. It was actually passing through. But this model is something that we say is pretty close to all the values that we are looking at. Okay. Now going back to my slide, when I say if the bias is high, it will cause underfitting. So first situation, the bias is high. That means errors of our, this is our predicted value. The red line is our predicted value. the cross is our actual value. So there is a lot of difference between the cross and our predicted line. In this case, the distance between our actual value versus the predicted is lesser. So this is something of a much better fit as compared to this. So going back again, that when our model is too simple, that means our model is not capturing the essential information. In that case, it is an underfit model. The model is missing something important. And if our model is capturing everything, but the model complexity grows, then in that case, the model is overfit. I hope that part is clear. So bias and variance usually have a trade-off. Trade-off goes like this represents the errors in bias. Errors in bias means, recall bias, I told you that what is my actual value versus what is my predicted value is the for the training data set. If there are errors, so when our model is very simple, let me take this up for you. Okay, so model complexity, it can be from a very simple model to a very complex model moving in the x-axis. The rate of errors is moving from very less number of errors to very high number of errors. So let us say our model is very simple as of beginning. In a very simple model, the errors due to bias will be very high. That means my model is actually having a lot of values which it could not capture. But as we keep on increasing the complexity of the model, the errors due to bias keep on decreasing. This you can also see with this equation, that when I'm increasing the complexity of the model, then the errors due to bias, the actual value and the predicted come so close that there is absolutely no difference between them. So this is what we are predicting, that error due to bias keeps on decreasing with increasing model complexity. But as we increase the model complexity, the errors due to variance, they actually start increasing. Now variance is a measure of that how close is our test data to the prediction. So training data was the one which we actually told the machine that this is the data that you learn from. But testing data is something that it has not seen prior. It is something new to it. It has to generalize. It has to actually be able to make the same prediction for something it has never seen. How is it going to, how good is it going to be? That depends on what is the error in variance. So error in variance usually keeps on increasing the way we increase the model complexity. Intuitively, if you look at this diagram, if there is a new value, let us suppose an x here, it would be able to generalize that also. But in case if there is an x here in the more complex model, it is saying, it is going to say that this value is something which is not fitting in my scenario, because I am fit to all the data which I have already seen, and this is the only data that I know. Anything new to it which does not falls on the line, it is something that I can't make predictions about. But this model will be able to make predictions even about those values which are a little far from this prediction line. So that is the point of being variance error being high. So optimum model complexity comes when bias and variance are both at a specific equilibrium condition, that we do not increase more bias or we do not have more variance. So bias and variance both being low, both being optimal, that actually leads to the minimum number of errors in both training and testing. I hope there are no questions so far. Let this sink in. If you have understood everything till the point that we have discussed, in that case, we can take it forward. So a model with high bias would always be away from the predicted values, will be different from the actual. But if the values are close by, very close by, all the predictions are close to each other, in that case, there is a low variance. All right. So variance is low, the values are close to each other. Variance is high, the values are very spread out. Bias is low, the values will be very close to the actual. The predicted values and the actual are very close. When bias is high, the actual values will be very far from the predicted value. इस केस में आपकी bias और variance दोनों high हैं. The values are scattered also and the values are away from the predicted values. And in this case, the bias is low, but the variance is high. Okay. So this is what we have discussed so far. Let us take it forward from here. Then, what is the purpose of understanding bias and variance, or how do you even utilize them? How do you calculate bias? The problem is big that I said I want to minimize the bias. I want to make sure the bias is lesser. How do I even calculate it? That is that I have to find out some way to find what is the difference between my actual and the predicted value. That basically is the computation that I require. So what we are going to take forward is if our model gets simple, the bias would get higher, the variance would get lower. If our model gets complicated, the bias would get lower and the variance would get higher, as seen from this. The model gets simple, bias gets higher, error due to bias, and the model gets complicated, the error due to variance gets higher. All right. We must find an appropriate point where bias and variance values are well compromised with each other. We can't lower both at once. Now, this discussion we are going to take forward is going to be about linear model, linear regression. But it's true for any machine learning model because all of the models have the same tendency that they will learn from prior data and they'll make predictions using that prior learned data about something that is unknown. So in the context of regression, models refer to mathematical equations which used to describe the relationship between two variables. As we already know, that any machine learning model is basically a mathematical equation by and large. There are some more additions to it, but for the sake of understanding, we can understand it as a mathematical equation. In general, these models from regression, they will deal with prediction and estimation of values. Like you want to predict what is the price of a house given what is the number of rooms, do they have a garage or not, what is the location they are situated in, then how furnished, well furnished is the house, then how many years ago it was built, is it new construction, whether there is a garage, parking or not. So all of these parameters are something with the help of which you will be able to predict the price of that house. Given that you know the prices of house in the vicinity, that a house which is 2 BHK in Rajouri Garden costs some amount of money, a house which is 3 BHK with parking costs some other amount of money in Rajouri Garden. So regression basically allows us to see that we want to predict or estimate the values of interest in our data. The prediction would be an output that, let us say we give that I have a 3 BHK house, I have a parking, the house is very well furnished. It was constructed in 2 years back. What would be the price if it is in Lajpat Nagar? So I would look at all the data from Lajpat Nagar. I would try to make a prediction, and the output would either come out to be exactly close to my actual value, or it would be somewhere different from the actual value. This difference is the one which we want to actually concentrate on. So models will look at all the aspects of data called inputs, जिससे आपके output effect हो रहे हैं, and then we use them to generate the estimated output. That basically is linear regression does. Or any machine learning model, again the same thing, that it would learn from the data and it would make a prediction if it is regression. Classification works differently, that you would learn from the data and then you would try to classify that into different classes based on what you have learned. Like cats or dog prediction based on the photographs, that would be a classification model per se. So linear regression can be in two forms. It can be a single variable, it can be multiple variables. Let us suppose this was the only input that we wanted to find out the height and weight relationship, that given somebody has this height, what would be the weight? Okay. We may have training data as heights and weights of a couple of thousand people. For each of them, we have a height, we have a weight. We can split the data into training and testing, and the training data is the one which we are going to feed it. So for all the heights, the model is going to learn what are the weights, and then it would create some equation like this, which is a model, which is called a model, which is a mathematical understanding of these were the height, these were the weight. My machine learning algorithm learned what is the relationship between them. And this relationship, it converts in the form of an equation. The equation can be as simple as linear regression in a single variable, but like we discussed housing prices, it could have been x1 could have been the number of bedrooms, xp could have been garage, there could have been what year it was constructed. Based on several factors, if we are predicting the house price, then that could have been again. The interesting thing here is I'm not saying it is y, I'm saying it is y hat. Y hat is a predicted output. The actual would have been y. That given my training data, I would have predicted y, or not predicted, that would have been actual value. So y hat is the predicted output, that this is something that my model is saying that given my height is 6 feet, the weight should be 90 kgs. That is the predicted output, right? But with 6 feet, my weight might be 80 kgs. My weight actually really might be 100 kgs. There is no rule about it. It varies from people to person, right? But we have to see how the predicted output is different from the actual. That is what we are going to look into. Right? So the concept is something that we call as a residual. A residual is something that allows you to understand that, let us go back to my previous question. The gap between my actual value versus what I have predicted on the red line, this gap is a residual. Okay. So our model is going to produce an output against any input. We can check these estimated outputs against the actual value that we tried to predict. So the difference between the actual and the model estimate is called a residual. All right. What do these residuals have to do with matrix? That's our next question. So first understand what a residual does. If our collection of residuals is small, that means the model that produced them, it does a good job at predicting our output of interest. Check the data back. Are there more residuals in this case, A, B, or C? You understand the definition of a residual. Quickly in the chat box, which out of A, B, or C you think there would be maximum residuals in? Would there be more residuals in A? This is A, this is B, and this is C. Which would have the maximum amount of residuals? Let me open the chat window quickly. Yes. From the participants, there's a question for you. Barkha, Jihan, M. Jayaraman, Minsa, Sandhya. Anybody? Where do you find there are the maximum residuals? Residual is the definition of, since I say my predicted value is the red line, cross represents the actual value. Residual is the difference between the predicted and the actual value. So which one of them has a maximum residual? Ashisha says A. Minsa says A. Anybody of a different opinion between A, B, and C? Okay, let us take it to be that residual would be maximum in this case, because we see visually we can actually describe that the distance between them is maximum. Here the distance is minimal. Minimal care, it might be actually zero also. So there is no residual here. Okay. So what we are saying that if our collection of residuals are small, the model that produced them does a good job. If the residuals are generally large, that model is a poor estimator. So we can technically inspect all of the residuals, like we plot all the points, we plot the predictions also, and we then try to compare all the predictions with the actual value. But what if we have thousands or millions of data points? We can't do this. It's not possible for us to be able to plot all the points, then plot all the uh, model values, and then take the distance of all of them and find out. We had only 5 or 6 different points, so there were only 5, 6 points. But what happens when I have thousands or millions of data points for which each of them I have to count what is the difference between the models predicted versus the actual value? I would not be able to do it. So statisticians developed summary measurements that take our collection of residuals and condense them into single value. That means, let us say I have thousands or millions of residuals from all the points which my data has. So I can consolidate all the values into a single value that can be representative of the predictive ability of our model. So these values are the metrics when it comes to regression. Mean absolute error is the first that you will discuss. Then there is mean square error, mean absolute percentage error, mean percentage. There is RMSE also. There are many summary statistics, each of them with their own advantages and pitfalls. Let us discuss them one by one. So mean absolute error is, okay, same diagram. This is the line of prediction. The line is now green instead of red. These are the actual values that we have in our training data set. The predicted values are all lying on the green line. So if I would have to say for the input value somewhere here, the output value would be only on the line, nowhere else. So for the input value which is here, the output value would be lying here. Okay. So mean absolute error is the simplest regression metric. What it says that calculate the distance between the actual point versus the predicted value. Predicted value is on green line. For this point, the actual and predicted have absolutely no difference. For this point, however, there is a small distance. For this point, there is a larger distance. The residual here is big, the residual here is smaller, and the residual here is 0. We take the absolute value of each of them because this distance is negative, this distance is positive, this distance is 0. Okay. When I convert these values to an absolute values, the negative and the positive residuals do not cancel out. Now, if I would not have taken a mean value or absolute value rather, then this point might have cancelled with this. Error to दोनों में है, that I have an error here, I have an error here, but for this point the residual is something positive, for this point the residual is something negative. Both of them may cancel out each other. Similarly, for these 2 points, the residuals may cancel out each other. To avoid that cancellation, because each of them is an error, we just take the positive value irrespective of whether the value is negative or positive, convert it to an absolute value, and take the mean of all the errors that we come across the different points in here. So mathematically, we can represent this as a simple data set equation which says that mean absolute error is that subtract the y hat, that is the predicted output value, from the actual. For each of them, take a sum, whatever the differences were from the previous screen. So for each of them, just subtract the actual from the predicted from the actual, sum them up, all the differences, and then divide it by the total number of points. So this division actually leads to the mean. So you are taking the mean of all the differences of the actual versus predicted, and this actual versus predicted you can also call as a residual. So you can say that we are taking a sum of all the residuals dividing by the total number of points. That actually gives me the mean absolute error if I am taking the absolute value of the residuals, not taking their sign. If it is positive, then we are taking it positive. If it is negative, then also we are taking it positive. Okay. Any queries so far? None. Not on the chat window. Thank you. So how do you interpret the mean absolute error? If the value of mean absolute error is small, That means the model is great at prediction. Well, if the value of mean absolute error is large, that means a model may have trouble in certain areas. MAE of 0 is the model is a perfect predictor. In the diagram C, the MAE value would be 0. But in real world, this does not happen. So in real world, most of the time, the residual would certainly be there. So MAE is easily interpretable because you can understand looking at the value that MAE is small, model is good, MAE is big, model is bad. Okay. But the absolute value is not often as good as desirable, while if we square the difference to convert it to a positive value, then it would be a better predictor. Now we say why better? Let us check out. There is a second parameter, second evaluation metric, which allows you to calculate the bias, which allows you to calculate the model performance, which allows you to calculate how my model prediction is different from the actual value. This you call as the mean square error. So mean square error is just like the MAE, but it would find the distance and square it for each of the values. So if the distance was +2, it would take the value as 4. If the distance was -3, it would take the value as 9, not -9, because -3 squared is 9. So automatically the values become positive when I'm taking a mean square error. So for this point, the mean square error would be small. For this point, the mean square error would be bigger if it's far off, but both of them would be positive for sure. Okay. So looking at the equation, we had the residual y minus y hat. We took a square of it first, and then after squaring it, we are dividing it by the total number of points. So compare it to the equation of the absolute mean absolute error, where we took the residual, we took an absolute value, and then we took a mean. Now we are taking the residual as in y minus y hat, squaring it, and then taking a mean of that. So the square of difference between actual and predicted is the square of residual. Now, how do you understand, interpret MSE? Because we are squaring the difference, MSE will always be bigger than MAE. Whatever be the value of MAE, except if it is 0, the MSE would be 0. But what if their MAE has a positive value, MSE would always have a bigger value. We cannot directly compare MAE to MSE. So it would be comparing apples and oranges. You can't do that. But how do you compare that model A? Let us say I was working with linear regression. Model B, I was working with decision tree. I want to compare whether linear regression works better for my problem or whether decision tree works better for my problem. I can't do that. So what I do, I calculate the MSE or MAE for linear regression. I calculate the MSE or MAE for decision tree, and I compare them. Whichever has a lower value is a better model. So we can compare model error matrix to those of a competing model. So this is something like that for two people running a race, they would be able to compare with each other, but for one person racing alone, you would not be able to compare it to any other person. All right. So for this reason, we cannot directly compare MAE to MSE because MAE is always bigger, or sorry, smaller. MSE is squared, so it is always bigger. We cannot compare them, but for two different models, we can compare their MSEs, we can compare their MAEs, and we would be able to say which one of them is better. There is another problem though. As you see that this actually squares the distance. What if there was a point somewhere here, which was way out of my total league? That would have been an outlier. So for the outlier, while the mean absolute error would not have been so punishing, the mean square error actually is very punishing because it would double that distance. So that becomes a very big problem, that if there are outliers in our data, with each residual in MA contributes only proportionally to total error. Wherever there is an error, in MSE it goes quadratically. It actually gets squared. So that is a problem with MSE. To counter this, there is another metric that we use as called root mean square error. So root mean square error is the square root of MSE. That means you first take a square, take a mean, but before taking a mean, you take a square root of the distance there. So the formula goes like, for mean absolute error, we took a mean value of the residual divided by the total number of points. Here, we are taking a sum of all the residuals squared, dividing by the n, and then taking a square root of whatever value that comes. So MSE, if you square root the MSE, it is going to give you RMSE. Right? Now, this is why is it used? Because MSE squared, its unit do not match that of the original output. Right? It could be length square or meter square if I was, or it could be the height of a person if I was trying to predict. Then while MAE would result in a height which is, the error would also be in the units of meters. In MSE, it would become meter square. We want to avoid that scenario. So because MSE squared unit do not match that of the original output, but MSE and RMSE both square the residual, they are both similarly affected by the outlier. So in this case also, the outliers are going to make a very big impact. All right. Sometimes you want to keep the outliers in ML, sometimes you want to throw the outliers away. Like in the height weight database, there may be a person which is having a very extremely long height. Maybe the person is 8 feet in height. So they are very rare people that way. So you might want to limit the number of outliers. You may actually take it off the data set. But in case of house prices, if there is a house in a locality which is a very highly priced house, in that case, it might affect the prices of other houses in that area also. So that is a scenario where you don't want to actually throw the outliers away. So you would keep them. There is another metric that we call as the mean absolute percentage error as per CBSE curriculum. Mean absolute percentage error is the percentage equivalent of MAE. So my first equation was MAE. If I convert it into a percentage, that is called mean absolute percentage error. So it is the ratio of the residual over the actual. I'll come to this in the same equation. So equation looks like that of MAE. Look at the equation. It says that instead of 1 by n, we are converting it to 100%. But there is an interesting point. The residual was there as it is. Before applying a mean, we take the residual and we actually scale against the actual value. We divide it by the original value y. Now this causes some problem which we are going to see. What if the value of y is 0? What happens then? In that case, MAPE value is not going to be feasible. Right? What if the value is very, very small? The y value is very small. So check out. MAPE is undefined for data points where the value is 0. That becomes a problem. MAPE can grow very large if the actual values are exceptionally small. That means if the value of y is very, very small in 0.002, 0.001, in that case, this total equation or total numerator by denominator, this actually terms goes high. So in that case, this value would become very high. So MAPE is also biased towards prediction that are systematically less than the actual value themselves. This we'll see another equation now. So for this formula again, let us assume that my y hat value was smaller than the actual. That means my actual value was 20, my predicted value was 10, and there was only a single variable. So in this case, y minus y hat would be 10 minus 10, whatever, because it's an absolute value, and 10 by 20 would be 1 by 2. This would come out to be 50%. So MAP is 50% here. The difference between them is 10 units, mind you. Okay. Now we are taking another where the original value was 10, but the predicted is 20. The difference is 10 again. But here it would be 2 by 1, and the MAP value would be 100%. So that becomes a very big problem when it comes to MAP instead of the other So MAP is not usually used as a parameter for model evaluation in the cases like this. Okay. One thing I wanted to tell further, we have discussed it for linear regression, but this is true for any regression-based machine learning model. The only thing that are going to change is these equations would be replaced by something more complicated. These diagrams would be replaced by something more complicated again. But the bias and variance remain the same as the terminology. This diagram would remain the same. The values would either be scattered, the values may either be concentrated. So everything else remaining the same. The only thing that is going to change is that which model are we applying. For SVM, it would be a different output. For linear regression, it may be different. For decision trees, it may be different. For XGBoost, there are several different models in machine learning. For each of them, we will be having certainly actual value. We'll also be having a predicted value, and there would always be some difference between them, which is going to allow us to understand that is my model predicting close to the actual, the output? Is my model predicting far away from the actual? And if we capture this gap, we will be able to predict the model performance, and that is why they are called the evaluation metrics for machine learning. I'm just throwing the house open for any questions that you have, and so that we can discuss them. Please post any questions that you may have in the chat window so that we can take them up. For the next session, we are going to cover a lot of metrics in the classification of machine learning, classification model. What most people get confused about is when to use precision, when to use recall, when to use F1, what is the difference between these, sensitivity, specificity, what are the differences between these, which one to apply when, and specifically there are case-based questions in CBSE which talk about that given this scenario, which particular evaluation model you are going to construct. So that would be the topic of our next workshop in this case. If you are interested in getting codes for these, please let me know, because most of the codes are single line codes for MAE, for MSE, for RMSE. So I'm not covered that with code because the code is usually easily available. But the conceptual understanding is the one which is most essential here.
So there's a question in the chat.
There are no questions on YouTube either. Okay, there is a. Subhashini said that this theory we have to explain using code or through the graph. Subhashini, I could not explain it without some things on the window. What essentially, if I have to teach it to any class, I would have to always tell them what is bias and variance. I would also have to tell them what do I mean when a model is simple or when a model is complex. Because this is the part which most of the books miss out on, that a model is considered to be more complex when I go from simple linear powers of x to square to cubes to quadratics or to even higher powers. The code, you would get only a value output with the code. For MSc, you would get a value. Let us say for the you get a value of MAE as 10. There is no way you'll be able to understand that what does this value of 10 mean. So this 10 actually is representing that the residual, the difference between the actuals and the residuals. And it would be very easy to show on a diagram that the residuals here are smaller. That is why the MAU value must be smaller. So the code simply outputs a single numeric value, which is very difficult to interpret unless and until the students understand the diagrams and the graphs prior. Then they can understand what the code output, how to interpret that.
Sir,
I hope.
can I ask?
Okay. Yes, please.
Sir, you are explaining this graph with the help of this diagram, right? So we need to have some data if we are explaining with this graph, or just by explaining simple fit, what actually they predicted, what actually the actual, and how it is been referent, and what is the residual. If we are explaining, is that much is enough as part as a CBSE curriculum is refers to?
Okay. So, ma'am, what you would normally do whenever you want to have actual data and show them this,
Mm-hmm.
you would create a scatter plot of the points. You would overlap a line of linear regression with that, and then you can always show them the distance between the actual line versus the point. That would be a residual.
Correct.
So that, and there are visualization tools which allow you to show what is the distance or the gap also that can be plotted. But
Okay.
that is mathematically, it's something like you are trying to draw a perpendicular to a line from a point and calculate the distance. So mathematically, that goes very complex for a student of class 10th or 9th.
So can
that
we
is
take
why,
this with Excel and then explain with this?
yes, you can. You can just plot a scatter plot. You can
Yeah.
plot the line of best fit, and then you can show them that these are differences are called the residuals.
Okay.
You can take data with outliers, and you can then show that the residuals are bigger in the case of outliers and the residuals are smaller in the case of no outliers.
Okay.
I'll show you one. Just let me bring in.
So can you please reduce the chat box so that your content is not able
Yeah,
to...
I'm just sharing some code with you for which I wrote some time back. So you'll be able to see the diagrams. Okay. So this is something that I drew about the matrix earlier. It's a bit
Because these concepts are new to the 10th standard kids. So how to
yeah.
make it interesting is really a tough situation.
See,
And we
this is
won't get maximum lectures. So just I want to make sure how we can actually deliver and make them understand in a sweet way.
see most of the time the perspective is enough that this much the student would be doing. They would take the data. They would do a 10 test split.
Okay.
Then you are going to call a model for linear regression. You call a
Correct.
model fit. You call a prediction. Okay. MSE is a single line of code. No problems here. Squared errors also you can calculate with the help of y test minus y predict raised to the power of 2. All right. Now I can plot both of them, the predicted versus the actual. All right. Just check out that when there are squared, I am putting them into colors. Where then if I have to show them the error bars in absolute error, so for a point which is an outlier, the error goes in big.
Maximum.
All right. So there can be, you can draw only the scatter plot, the actual values and the predicted values on the red line. That also goes well. Okay. Or you may draw multiple, like this is with RMSE. All right.
So could you please share this in our group?
Yes, yes, I would be. Don't worry. This is something that I did for.
No, for our better understanding, also we have to do some exercises before we teach.
I'll try to make a simpler one. In the meanwhile, I'm just keeping this on the record for you.
Yeah.
So that you can use it. But I hope to come up with something which is even more simpler than this.
Okay.
This is a bit.
So we can do in Excel because Excel becomes easy for them to type and they will get the graphs immediately.
Yeah,
We can explain
I'll.
easily.
Okay.
Then we can go for Python. So then they can easily write the code and they can connect.
I have just shared it on the chat
Okay.
box. You can copy the link. This is available for everyone.
Okay, so thank you so much.
Yeah, sure. So this is a bit complicated. This is not very easy. I'm just making it available so that you can play with it. I don't mind. All right. I tried to generate some synthetic data with outliers also. So you can use this data. You can use the part of this, that how do you create data with outliers. And then you can try to make a model of best fit, because the line of best fit would be coming here. So some of the points would have a larger distance with the line of best fit. And that would come up in MSE or RMSE for that matter. So RMSE and MSE would be increased. But if you remove these outliers, you would have a line of best fit with MA doing very well. All right. Any more questions? Okay. Thank you so much, Subhashini. That's the basic purpose of why we are trying to work with the faculty. There are points which are teaching machine learning to higher education gives me a different perspective, because the kind of query the students ask in classroom when they are undergrad, they have a very high level of queries, but making it simple so that class 10th and 9th students can understand, it's a bit typical. Visualization is the best, Subhashini, as you inquired. Okay, so I'm just closing this. This is available with you for the error matrix, so you can use it. If you want the slides also, I'm just going to share the file. There's your slides. Thank you so much for the time today. And we look forward to having all of you in the next session when we come for classification metrics like precision, recall, F1, all of them in the next session.
Thank you, Dr. Gupta, once again for a highly informative and interesting session. And thank you, everyone who joined in. As Dr. Gupta said, we'll soon be having another session for class 10, about which you will be notified, as always. Have a great weekend ahead. Happy Holi, everyone. Thank you.